Hi everyone, welcome to Random Thoughts with Alex. This is part 2 of a series about the Lorentz-ether theory. If you haven't already, I suggest you watch part 1 first. The link is in the description. In this video, I will derive the equations for relativistic mass. This video will be somewhat more technical than my other videos. Some knowledge of calculus will be needed. The Lorentz-ether theory is a theory that reproduces many results from special relativity, but starting from absolute space and time. It is also assumed that velocities are additive in the same way as in Newtonian mechanics, even at relativistic speeds. It assumes that the principle of relativity is an emergent law, not a fundamental law. My version of the Lorentz-ether theory is different from the original version in that I start from the iconic Einstein equation, E equals mc squared, as an axiom, not something we derived from other properties of electrodynamics. And because we assume absolute space and time, and because we don't adopt Minkowski space, we can legitimately distinguish between rest mass, the mass of an object at rest, and relativistic mass, the mass of that same object moving at relativistic speeds. In a nutshell, the argument goes like this. When we accelerate an object, we add energy to it, making it heavier. And because of the extra mass, we need more energy to accelerate it further than will be needed in Newtonian mechanics. Under these assumptions, we will show mathematically that there is a limit velocity that we cannot exceed. That limit is the speed of light. To translate this into math, we will need calculus and some mechanics. Let's start with Newton's second law. F equals m times a, where F is the force, m is the mass, and a is the acceleration. By definition, acceleration is the change of the velocity per unit time. A equals dv over dt, where d represents an infinitely small increment, v is the velocity, and t is time. The second law becomes F equals m times dv over dt. But this is only true when m is constant. If m is not constant, then the force is the change of m times v per unit time. F equals d m times v over dt. Physically speaking, what that means is that we need extra momentum to pick up mass from the ether and bring it up to speed. This is one of the reasons you don't hear about relativistic mass in modern relativity. It is closely tied to the concept of an ether. Now let's get to the derivation. Consider an object with mass m0 at rest, in other words, at v equals 0 in an absolute frame of reference. The mass is pushed forward with a force F, causing it to move. The evolution of the velocity of the object is what we've just seen. d m times v over dt equals F. We only consider the force in the direction of the velocity. The energy change of the object is the work applied to the object, in other words, force times displacement. dE equals F times dx, where x is the distance traveled by the object. And the distance traveled by the object is velocity times time. dx equals v times dt. When we combine the last two equations, we get dE equals F times v times dt. Next, we solve for f. We get F equals dE over v times dt. Let's go back to our modified second law. d m times v over dt equals F. We substitute F in this equation and we get d m times v over dt equals dE over v times dt. we can eliminate the factor dt on both sides of the equation. dm times v equals dE over v. Now we need to use a trick from calculus known as the chain rule. dm times v equals m times dv plus v times dm. We use this to expand the differential of m times v. m times dv plus v times dm equals dE over v. Now we introduce the Einstein equation E equals mc squared. In differential form, this becomes dE equals c squared times dm. Substitution into our result leads to m times dv plus v times dm equals c squared times dm over v. Take v times dm to the right-hand side. M times dv equals c squared times dm over v minus v times dm. Let's put this last term into the fraction. M times dv equals c squared times dm minus v squared times dm, all of that divided by v. And we take the common factor dm out of the fraction. M times dv equals c squared minus v squared over v times dm. To solve this equation by integration, we have to separate the variable v from the variable m. This leads to v times dv over c squared minus v squared equals dm over m. A useful equation in calculus is dv squared equals 2v times dv. This allows us to rewrite our results as 1/2 times dv squared over c squared minus v squared equals dm over m. We take the integral on both sides, from velocity 0 to v on the left-hand side and from mass m0 to m on the right-hand side. 1/2 times the integral from 0 to v of dv squared over c squared minus v squared equals the integral from m0 to m of dm over m. Mathematicians may not like my notation, but the intention is clear. Integration leads to minus 1/2 times ln c squared minus v squared over c squared equals ln m over m0. Working out the fraction in the ln leads to minus 1/2 times the ln of 1 minus v squared over c squared equals the ln of m over m0. This can also be written as the ln of 1 over the square root of 1 minus v squared over c squared equals the ln of m minus m0. The logarithm can be removed by taking the exponential on both sides. 1 over the square root of 1 minus v squared over c squared equals m over m0. And this leads to the relativistic mass equation, m equals m0 divided by the square root of 1 minus v squared over c squared. Let's introduce the Lorentz factor. Gamma equals 1 over the square root of 1 minus v squared over c squared. Then the relativistic mass can be written as m equals gamma times m0. It is useful to consider the apparent Newtonian inertial mass of a moving object subjected to a force. It is useful to consider the apparent Newtonian inertial mass of a moving object subjected to a force. We will need it in future videos. To that effect, we go back to the revised second law of Newton. F equals d of m times v over dt. And we can apply the chain rule. F equals m times dv plus v times dm over dt. If the force is perpendicular to the movement, then the motion is circular and the value of the velocity, and hence the mass, does not change. But the direction changes. For that reason, it is best to use vectors in the equation. Vector F equals m times d vector v plus vector v times dm over dt. But because the mass is constant, dm equals 0, the equation reduces to vector F equals m times d vector v over dt. This is Newton's second law in its original form, and it follows that the inertial mass of an object subjected to a tangential force, that is, a force perpendicular to the motion, is simply the relativistic mass. We'll call this the tangential inertial mass mt. mt equals m, which equals m naught divided by the square root of 1 minus v squared over c squared. Or mt equals m equals gamma times m naught. If the force is in the direction of the movement, we need to consider both terms in Newton's second law in revised form. We no longer need vectors because the direction doesn't change. F equals m times dv plus v times dm over dt. We substitute the equation m equals gamma times m naught. This leads to F equals gamma times m naught times dv plus v times d gamma times m naught over dt. The rest mass, m naught, is a constant, so we can take it out of the differential. We don't need to use the chain rule. F equals gamma times m naught times dv plus v times m naught times d gamma over dt. Remember, gamma equals 1 over the square root of 1 minus v squared over c squared, which equals 1 minus v squared over c squared to the power of minus 1/2. And gamma is a function of v only, so the differential of gamma is d gamma equals minus 1/2 times 1 minus v squared over c squared to the power of minus 3 over 2 times minus 2v over c squared times dv. The first factor between brackets is gamma to the third. Also, we can cancel out the minus signs and a factor 2 in the numerator and denominator. That leads to d gamma equals gamma cubed times v over c squared times dv. We substitute that into our earlier equation and we get F equals gamma times m naught times dv plus v times m naught times gamma cubed times v over c squared times dv divided by dt. We can take gamma times m naught out of the fraction and separate dv over dt. This leads to F equals gamma times m naught times, opening bracket, 1 plus gamma squared times v squared over c squared, closing bracket, times dv over dt. Writing the Lorentz factor in full leads to F equals gamma times m naught times, opening bracket, 1 plus a fraction within the numerator v squared over c squared, and in the denominator 1 minus v squared over c squared, closing bracket, times dv over dt. We bring everything between brackets into a single fraction. F equals gamma times m naught times a fraction within the numerator 1 minus v squared over c squared plus v squared over c squared divided by 1 minus v squared over c squared times dv over dt. There are two terms in the numerator that cancel out, so what remains is F equals gamma times m naught times 1 over 1 minus v squared over c squared times dv over dt. What's left of the fraction is the square of the Lorentz factor, so the equation becomes F equals gamma cubed times m naught times dv over dt. We find that the longitudinal inertial mass, which is the apparent mass when an object is pushed forwards or backwards, is the Lorentz factor cubed times the rest mass. ml equals gamma cubed times m naught. Or ml equals m naught divided by 1 minus v squared over c squared to the power of 3 over 2. We will need the longitudinal mass and a tangential mass when we calculate how the relativistic mass affects the dynamics of mechanical and electrical systems. This will lead us to the conclusion that, in the framework of the Lorentz-ether theory, time dilation is just a physical slowing down of physical processes and not some mysterious property of time itself. That's it. I hope you enjoyed this video. If you did, please like and subscribe, and I'll see you in the next one.